Hello, can people hear me?
Yes, bro.
Oh, okay. I've got a new microphone. It runs off a battery. We'll have to see how long it lasts. So if the sound disappears, please let me know. Okay, everybody, we thank you for coming, and we'll go straight into the presentation. Right. Some of you will have heard this before, but I have updated it, so I hope it will be of interest. Okay, and this time I've actually called it preparing your data for analysis before it's even collected. And I'll explain in a second why I'm going to say that. As you can imagine with your research, I mean, this is in a very rough outline what you're going to do. There is or are data out there. You're going to collect the data, record it, in due course, present it for analysis, and then analyze it. In order to analyze it, it has to be in a fit state to be analyzed, which I've called that present for analysis. And we're actually going to start by talking about that. But the point I want everybody to remember is that if data is going to be presented for analysis eventually, it makes sense to collect it and record it in a particular way. So a good research project, a lot of thought is given as to how the data will be collected in terms of how it will be analyzed and presented for analysis right back at the start of the project. People do like to rush into data collection, but it's actually not a good idea. We're going to spend a bit of time now talking about how data should be presented for analysis. But the message behind that all the time is, remember this when you collect it. Remember this when you collect it. I'll certainly give examples of data, that were collected in a manner which in fact closed off promising lines of analysis. Once it came for analysis, it was too late. The data had been collected in such a way that the information was lost. Right. So the first thing is formatting your spreadsheet for analysis. Now, I quite often help people with their analysis and with their stats. And one of the first things that always happens is they bring me 3 or 4 or 5 or 6 or 7 spreadsheets with calculations on them and titles and little stories, none of which are actually suitable for analysis. And we spend a good few hours just trying to get the data into a form which can be analyzed. And that's really what we're going to talk about now. Formatting your spreadsheets correctly. Okay. Now, the first thing is if we're going to do any sort of statistical analysis, data must be presented in a spreadsheet format. That's so that we can manipulate it mathematically and statistically. And because statistical software, almost all of them without exception, are able to import an Excel spreadsheet. And then they use that as the basis on which their calculations take place. Now, the next thing is that this data has to be on a single worksheet, unless there are compelling reasons to spread data across several sheets. That's not a single file. That's a single sheet in Excel. Okay, unless there are very compelling reasons to spread the data across several sheets. Always try and get it onto a single sheet. Sometimes it's possible to summarize data by importing it from several sheets onto a single sheet for analysis. There's a good reason for this. Stats packages can work on only one sheet at a time. So if you want to do an analysis involving variables which are on different sheets, well, you can't. So always try to get all the data collected onto one big single master sheet. Next thing is that stats packages demand a very simple spreadsheet format, but they don't like any deviation from that very simple format. Rows and columns. The top row, that's row 1 on your Excel spreadsheet, is for headings, nothing else. With Excel, you can put data wherever you like and you can still do calculations. But stats software imports the spreadsheet and looks for row headings in line 1. Okay, row 1 is where it looks for the names of your variables. So the top row must contain variable names. There's one column per variable. In other words, one column for age, one column for gender, one column for ethnicity, one column for university, etc., etc. Single column per variable. All the other rows except the first one actually contain your data. So your first subject will be in row 2, your second research subject will be in row 3, and so on down the end to the end of your research subjects, with no other rows and nothing else in between. You start at row 2 for your first subject, and you end at row 501 for your 500th subject, not on row 502 or 504 because you've left blank rows or have put in headings or something like that along the way. And the final point is one usable item of information per cell. That's all stats software can handle, and we'll show examples of that. Right. So this is what the statistician needs to see. Very simple. The first row is the names of the variables. Okay. First column is not essential, but yeah, we've got our identifying data, the name or ID number or research number, what have you, of the subject. And the other columns are variables. This, for example, is glucose levels. There's a control column for our control subjects, and there's a diabetes column for our diabetes subjects. Which, by the way, makes another point, which I haven't actually written out specifically on a slide. When you do analysis, you're going to be going back to these variables to find the right column repeatedly and repeatedly. The shorter, more self-explanatory and succinct you make the name of the column, the variable, the easier it is to find your way around. So go for very simple, short, punchy variable names that tell you exactly what it is. People often come to me with questionnaires and it says question 1 and question 2, and it's all very well, but often it makes far more sense to give a name to question 1, like gender. Question 2, education. Question 3. That's so that when you do analysis, you can compare gender with education and you don't have to remember what question 1 is and question 2 is when you do the comparison. Right. Software, as I said, looks for variable names in that first row. So I now want to do a t-test. I go to my package. I click on that drop-down list for variable, and there's my choice. I can select control. I can select diabetes. I can select subject. I select control. I select diabetes, and boom, off goes the software, and there is my answer. Very quick and very simple. And now look what happens if you present the typical Excel spreadsheet. The data starts somewhere on line 6, and the first few rows are given over to little explanations and titles and stories and units and what have you. I try to analyze that. I try to open the name of the variable, and my software tells me, gives me a choice of diabetes study, first run, and May 2023. Because those are in the first row, it thinks those must be the names of the variables. So that is why we cannot have little stories written in the first few rows. Row 1 is for variable names and nothing else. In fact, in general, don't write little comments and explanations and stories and keys and things on your spreadsheet. If you must, put it way over to the right, where it can't be confused with being an actual variable. You'll also have to keep it out of row 1, otherwise software will see it as a variable. This is another important point, okay? When you do the analysis, it cannot be submitted with calculation rows. You see at the bottom, we've got a total and we've got an average. That's fine if you're only working with Excel. But as soon as you import into a statistical package, you run into this problem. Control, it says there are 29 data points. But if I count my subjects, there are in fact only 27, row 2 to 28. It says the maximum is 147.987. Well, I don't see a glucose higher than 7.2, I think it is. And what's happened? The software has seen the number 148 in the column labeled control, and it has treated it as a data point. So it's actually been included in the analysis. And that's why you can't have totals and averages and other calculations on your spreadsheet in the same columns that you're actually going to use for analysis. The software does not distinguish between data and calculation type stuff you've added in. It'll just incorporate it into the analysis. And then as you can see from those maximums, the results, of course, become nonsensical. The next thing is how data are formatted. Start with numbers. I'll give examples of all of these in a second. But there should be all numbers or all text in a column. Okay? Stats can do certain tests on text entries, like the name of the university. Example would be chi-squared. It can do other tests on numbers, for example, t-tests and analysis of variance and correlation and so on. So all numbers have to be in the same format. It's very common that people present to me a column that says age, and along with 3 and 20 and 25 is 3 years, 6 months. Absolutely no way that software can handle that. Can't muddle up text and numbers in the same column. You would have to convert that to 3.5. And then you have to decide if it's appropriate to start using decimals. If you have to put 3.5 for that person, then everybody else should be 27.0 or 12.0. Got to decide exactly what precision you're actually going to use. Another one to watch out for, and I've been caught this way before. Numbers must be numbers, not text that looks like numbers. Here's an example. Age 48. That's a real number. I can talk about me being older than the person aged 48 because my age is higher than theirs. I can talk about most of you being younger because your age is less than 48. I can take that age 48 and everybody else's ages and do a calculation and come up with the average, the minimum, the maximum, etc. But also in life, we use plenty of numbers that are not really numbers. They are labels, they are text. Classic example is a phone number. 07623499695 looks like a number, but it isn't. We never add up a whole bunch of cell phone numbers and then find the average. We never add one cell phone number to another. We never multiply it by anything or put in a decimal point. And another one would be a car registration. ND340926. That's not really a number. So unfortunately, it's quite possible for stats software to get confused between the two. And sometimes you're not even aware that it's happened, but it's actually recorded somewhere in the back of the spreadsheet where you don't see it, that it's been labeled as text, not a number. And if so, software is going to ignore it in calculation. And I've been caught this way. I've just suddenly noticed after doing my stats that it says sample count 23. And I said to myself, but hang on, I've got 35 data points. And I discovered 12 of those apparent numbers had somehow been labeled by Excel as text. They look just like numbers. Excel called them text, and they were excluded from the calculation. Right. All of these we're going to show examples in a second. The next is when you are labeling things by a class, which university are you, or which gender are you, or which ethnicity are you, or are you a student or a lecturer? You must standardize the labels you use. If it's UKZN, then every one of your subjects who belongs to UKZN must have UKZN written in that column, not UKZN with a space, and then sometimes U with a space, then KZN, then sometimes U full stop K, full stop Z, full stop, and so on, sometimes UNIV, KZN, etc. And watch out for typos, like writing ULZN. Watch out for extra spaces before or after the name. The reason is that software will not know that U space KZN is the same as UKZN. It'll separate it out into a separate class, and it'll analyze it as a class on its own. It will go missing from your UKZN results. Also, and I'm going to examples of this, a common thing is to put multiple text values into a single column. So our students ask the patient what drug they're taking, and then in one column they write the names of all the drugs. It's almost impossible to analyze as to which drugs are being taken. Place them in separate columns if you want to count or analyze them separately, and again, I'll give an example of that. So let's start with this one. Beware of numbers incorrectly formatted as text. On the left is age, and that's exactly how we want it. On the right is age, but unfortunately, a number of those entries have been mislabeled as text. Sometimes you can pick that up because in Excel they now become left aligned like text rather than right aligned like numbers, but that's not always the case. Here, I've done a summary of the statistics of both of those columns. And you can see the one on the right, on the left, has correctly picked up a sample size of 20. The one on the right has only picked up a sample size of 13. And the reason is it's excluded numbers rows 5 to 11, which it regards as text, like a cell phone number or a number plate, and not as a real number, which can be added up and divided and averaged. So watch out for this. One of the best checks is whenever you do a statistical test is to check that N number and make sure it's correct. If you know you should have 20 data points, make sure it says N is 20 and not 13. Whenever the number the stats package spits out is less than the data number you're expecting, always go back to your spreadsheet and find out what's wrong. The stats package doesn't get it wrong. If you look carefully enough, you will find something that is misformatted, and then you change it back on the spreadsheet and then report it and work again. This one we mentioned. Don't mix formats. So we've got 18, 30, 31, but we've also got 4 years, 6 months. We've also got more than 50. We've also got 204 months. And when you do any sort of stats calculation, those three will be excluded. The software cannot, add 4 years, 6 months to 18. It can't add greater than 50 to 30. It can't add 204 months to 60. So absolutely essential that all that data is standardized, all as numbers, if necessary with a decimal place. The next thing, as we mentioned, is that the data in each cell must be standardized. Just look here, this is different universities. Whoever captured this has sometimes called it UFS, sometimes small letters UFS, sometimes just FS, sometimes Free State with small letters, sometimes Free State with capital letters, and so on and so on. I'm going to do a chi-squared on this just to see how many people come from each university and break it down by gender. Whoops, what on earth is going on here? Well, you can see what it is. It's regarded Free State as a separate category from FS, as a separate category from UFS. This particular software I've used is forgiving, but others will even distinguish lowercase UFS from uppercase UFS and regard them as separate cases. So this is now nonsensical and absolutely uninterpretable. If we go back and very carefully make sure that we use the same code, UFS, every time somebody comes from UFS, then calculations will behave. And now we can see very nicely the breakdown of our subjects by gender and by university or school. Always remember that. There's a huge temptation when, or chance of error, particularly when people write things in by hand to data collection sheets or have to type things in by hand. There are ways around this, one of which, of course, is to have drop-down menus so that people can only select UFS and there's no opportunity to type in U spacebar FS by mistake or UFS full stop by mistake, which will also be picked up as a separate class. And here's just another example. There are 4 schools in the College of Health Sciences, and we want to find the average mark of our students and tests. Mark and school come up very nicely. I can do a t-test, at least an analysis of variance, and I get a very nice result. And if you look down there under factor, over here, you can actually see that it's got 4 schools. As soon as somebody starts to mistype things like this, okay, sometimes they call SCM ClinMed, sometimes SLMS is called SLMMS, sometimes SLMS, sometimes LabMed, then again you get this sort of nonsense. It's done analysis of variance regarding every single one of those different typing formats that's being used to name schools as a separate class. So again, absolutely essential. Now, I can remind you just to use a single code, but very often what happens is that a little typo creeps in as you put in that single code. A space bar creeps in, a comma creeps in, a letter creeps in, a quote mark creeps in, but just because of fumbling while you type. Now, with a calculation like this, it's going to be pretty obvious. The problem is that when we go back, often we have to, in fact, I should have put an example of this. Often we have to limit the type of data that we want to do the calculation on. Okay. And you do that by setting your criterion. I think this is so important that I actually better show it. And if you've typed something wrong, then it won't show up in that grouping. I'm actually going to pause for a second and try and demonstrate that because it really is very important. So just give us a second. Okay, I'm afraid I'm going to give up on that one. I just can't find a nice spreadsheet to show it on. But the bottom line is, if we wanted to compare two of these schools, okay, the way it would be done is that the software would ask us where are the values to compare, which would be the variable called mark, and it would ask us which variable tells you the classes, what we call the factors, okay, that distinguish the different groups. And that would be school. And what we then do is we limit school equals SHS, and the other school equals SNPH. And then it'll compare all these values where the school equals SHS with all the values where school equals whatever it was, SNPH. If any of these have been misspelt, then it's going to leave it out of the calculation. And again, you're going to end up with erroneous results, and that you may not notice unless you look very carefully at the number of entries in each group, where you may notice that it's only 58 instead of 60. And the reason is because there are 58 SCMs, and there's one SCM full stop, and there's one comma SCM. Those will have been excluded from the calculation. So I'm sorry I couldn't demonstrate that. Something needs to be in the slide for another time. This is also something that can be very, very tricky. It's not well understood, but very simple. Even Excel, but particularly software, distinguishes between blanks and zeros. Okay, here's an example. So here we have a column called age. There's a number in every one. Okay, and it's counted 24, which is correct, and it's done appropriate calculations. But let's say that 4 of our data points are missing. For 4 of our subjects, now we have everything else, but we didn't record age. It was left out. Now, this is what we want to happen. The calculation should be done on 20, not 24. Okay, and that's quite correct because these have been left as blank. This is hugely dangerous. Somebody has put in 0 for the ages. Software sees 0 as a number, so it thinks there are 24 data points, and it's done all the calculations on that full 24. You can see I've picked up a minimum of 0, which of course is completely wrong. There were not 4 people aged 0 years. There were 4 people who did not have an age. This is something else people like to do. They write little comments, dashes, not dones, question marks, n/a, right? Most software will just ignore those. The reason being that it sees those as text, not as numbers, but it doesn't know that those are really blanks. Here's Excel using one formula for count. It's picked up 20, but there is an alternative formula for count, called count up, by the way, which is returned 24. And the reason is that records all cells that are not blank as being important or meaningful. So it regards these 4 cells as being valuable or meaningful and containing some sort of data, even though it's a different data to the rest. And that's not what we want. This is the column we want. So if data is not available, it should be blank. And everything on which there is data should have something written into it. Everything for which there's no data, there should be nothing written into it. Now, this one is a point I've actually made several times. Always capture all the detail possible. Don't discard detail before analysis. Okay? You can always discard it during or after analysis, but even then you won't delete it permanently or keep it. But the trouble is when people capture data in some form of abbreviated manner, and I'll give examples, and then you can never recreate it subsequently. Valuable information may be lost. The one I've mentioned several times now on these lectures is lumping things together. Okay? So here is some sort of test result. And what we've done is group people by age, 40 to 49, 50 to 59, 20 to 29, etc. Now, the only stats you can do on that is basically comparing different groups. That would be an analysis of variance, and I've done that here. Now, just to eyeball it, it does look as though the numbers are going up with age. We can do the statistical analysis, and sadly, it's not significant. P equals 0.093. However, if instead of that, we had actually captured the real age, as in the first column, then we can do much more subtle statistics. We can do a scatter plot correlation of age versus result. The software will draw the regression line. You can see it's going up, and it's done the statistical calculation. This is the Pearson's correlation. It can tell us that it's significant. It really does rise with age, and it can give us the extent of the correlation, R equals 0.31. So there's very valuable information in this that was not apparent when we grouped things. If you've got ages like the first column, you can always group them later if you can think of some good reason to do so. But if you've captured the data as in the second column, then you can never untangle or ungroup it later. And as I said, you've lost valuable data. So be extremely careful about lumping things together. Rather write down the original value from the start and keep it like that. Okay. Many laboratory tests, let's say some sort of theta is returned. Then don't write down positive or negative. Write down 3, 5, 27, 13. Even though you know that anything less than 10 is defined as negative and anything greater than 10 is positive. There may be very, very valuable insights to be gained by comparing those actual numbers with something, rather than just comparing positive with negative. Right. Okay. So work from original data. Don't lump things. Okay. Bring original data to the statistician, not stuff that you've sort of tried to pre-digest. Okay. And don't replace original data with summarized or simplified data, age group, averages, totals. For example, I've had med students who've done some sort of test with their subject, like they've taken a group of doctors or students and subjected them to a little exam to find out how much they know about, for example, skin disease. But then when they come to see me, they can't tell me what mark each person got for question 1, which was lupus, question 2, which was syphilis, and so on. What they've done is averaged all those results and then thrown away everything. So they come to me with the averages, but we can never now go back and prove, for example, that most people know more about syphilis than they do about systemic lupus erythematosus. If we had that original data, what they said for each question, it becomes possible. If that stuff has been thrown out and just an average for all the answers brought to me, valuable data is lost. Now, this is another common one. It is possible to untangle, but it's extremely difficult. Okay. This person has decided to make a list of the drugs that each of their research subjects is taking, along with many other columns, which we don't show here. So, first chap took erythromycin, but the third subject was on 3 antibiotics, metronidazole, erythromycin, and ceftriaxone. And it's the same with many of the others. And sometimes metronidazole is the first name on that list. Other times it's in a different position, like there it's number 2. It's extremely difficult to do any sort of analysis on this. How many people were on metronidazole? How many people were on 2 drugs? How many people were on the specific combination, azithromycin, metronidazole, and others. Very, very difficult to work out from this sheet. It can be done, but you've got to be a real fundi at Excel. And if you've got hundreds of subjects, you're really going to struggle to try and do it manually. If, however, you had captured the data like this, are they on penicillin? Yes, no. Are they on ceftriaxone? Yes, no. Are they on erythromycin? Yes, no, etc. Then, in fact, it becomes extremely easy to extract totals. 15 were on erythromycin, 8 on penicillin, 13 were on erythromycin and metronidazole, and so on and so on. Plus, it's very easy to total each of these columns to find out how many were on penicillin, including penicillin and something else, and so on. Now, this does require that you know in advance which categories are important. Watch out for other. It may well turn out when you come to do the analysis that there could be a very interesting trend under other. But the trouble is, we don't know what drugs these people were on. We just know it was other. That's another classic example. Whenever you have a column that's other or not otherwise specified, add a text column where people can write in the names of the other things. Because if it then becomes apparent later that there may be something interesting there, you can take that particular column, for example, the drug tetracycline, and you can make a column for it and transfer everybody who was on tetracycline into that column as an N or a Y, and we can now add that into our analysis. So, other on its own can lead to serious loss of information that may only turn out to be important when we do the analysis. And if it wasn't captured at the start, it can never be captured again unless you are prepared to go back and re-find your 500 subjects and ask all of them just that one question. You said you were on another drug. What was its name? So watch out for that one. Right. So now you see all the things that have to go into the spreadsheet that you present for your analysis. So now we're going to talk about designing a data collection sheet. I think the point we're making is as you collect your data, you've already got to be thinking ahead as to how you're going to be using it. If you correct the wrong data in the wrong format or the wrong way, as I've given examples, when you come to the analysis, at best, it's going to be more difficult. At worst, it's going to be impossible. Important information would have been lost. Right, so you must understand what you're going to do very thoroughly. He has this famous quote from Alexander Pope, "Fools rush in where angels fear to tread." Don't rush in to deciding what data to collect. Don't rush in to designing a data collection sheet or spreadsheet or database or even word form, whatever it is, until you've actually thought far ahead as to what that data is going to be used for. So your data collection sheet is the template. It's going to guide you in what information you want, in identifying what information you get, and recording it. Okay, that's your research data at its source. But ultimately, at the end of the day, that's going to have to be used for analysis. If, for example, your data is on sheets on which people tick things or write in numbers, at the end of the day, that's going to have to be transferred onto an Excel spreadsheet, or if you fancy, into a database or something. Right. Now, there are some huge dangers in all of this. First, the well-known GIGO, garbage in, garbage out. This is particularly the case when you get somebody else to collect your data for you. If they mess it up and make mistakes, your data becomes useless. I'll give an example of this. And the second thing is the lost opportunities. You come to me with your data classified by age group, and we say, if only we had collected the age and not characterize people by 20 to 29, etc. Think of the more powerful, complex, rich, interesting statistical analysis we could have done. So these are things to think of right at the start as you design your data collection. So always specify your intentions. Why do I want to know this? How am I going to use it? Look ahead to the analysis. Am I going to want to compare yeses with nos? Okay, like how much alcohol, do you drink alcohol? Yes, no. Or are you going to say, how much alcohol do you drink? 0 units per week, 1 unit per week, 2 units per week, etc. And I think you can see by now that data collected as units per week, provided it's accurate, is far richer in terms of the analysis that we can do than drinks versus does not drink. There's a huge difference between somebody who drinks 1 bottle a week and somebody who drinks 20 bottles a week. So think about those things at the start. And if you want to say yes or no, decide. Wouldn't I actually rather know the underlying data? Instead of adult versus child, put the age, and so on, and so on. So the thing must be designed, it must be appropriate for your question or your intention. It must be formulated appropriately for the analysis you will do to answer that question. You may, for example, have to decide and standardize whether you are interested in age in terms of years, which actually is a form of lumping, or age in terms of months, which gives you 12 times the range. Okay. If, for example, let's say you want to know how many years of experience I've got. If you just put years, we compare 1 year with 2 years. If you put months, we can actually compare 2 months with 10 months. We can compare 2 months with 23 months, and so on. You can see again how much richer that information is. If something changes during your training, during your experience, instead of just saying, well, it was absent in year 1, it's present in year 2. If we've collected months, we can actually say, around about the 6th month, we notice a change happening. People with 0, 2, and 3 months score very poorly. Those with 7, 8, 9, and 10 months score very well. And between 4 and 7, we see people starting to improve. Much richer information. So you all know the well-known FIFO, which of course is rude, so I won't say it out loud, but I've got my own version of it here. Fuzzy thinking in, fuzzy results out. If you're not at all clear what exactly it is you're trying to collect and what you're going to do for it, you're going to end up with fuzzy results that it'll be difficult to analyze with the clarity that we really would like to do that. Okay. Now, always minimize potential for error in data collection. Always consider third parties, the person who might collect data for you, the person who might capture your data for you. We're all human. We all make mistakes. And we also know, we've all had hundreds of examples, how people can be absolutely blind to how confusing something can be for someone else. So someone else asks you a question. We've all had this with university exams, okay? You get asked a question. Presumably you ever set the question, knew exactly what they were looking for. And yet as students, we look at that question and now we're really worried. Is he asking for this? Does she mean that? And so on, and so on. So this can absolutely mess up your data. For example, here's a questionnaire, and we've asked a research assistant to go out and question students. And one of the questions is question for sex, and there's a space for the answer to be written in. So you get this back. You now belatedly think to ask the research assistant what she means, and she says, I assumed it meant biological sex. And you say, Yes, that's right, exactly what I meant. And you see you've actually got 30 data points there. You ask the next research assistant, what on earth is going on here? Yeses and nos. She says, oh, I thought it meant, are they sexually active? So I wrote yes or no. How many data points do you have? 0. Okay, into the trash can. Because you cannot, there's no way you can convert that back to male or female, short of going back to every one of those original subjects and asking them again. What about this one? It looks similar, but when you ask the person, they say, oh, sorry, I thought it meant self-identified gender, not biological sex. Some of the people I examined looked male, but they were wearing dresses, and they said, no, thanks. They would rather be identified as female, so I put them down as female. And that's all very well if it's some sort of sociological study. But if we are looking at something that's closely related to biological text, like testosterone levels or something like that, then this data is useless. And because we don't know which of those data points are the ones that say female when biological sex was actually male, we have to throw the whole lot out. So once again, they all go into the trash. So it's extremely easy for people who assist you, third parties, to misinterpret your questions. And if there's doubt about any of the answers, then sadly, you have to throw the whole lot out, unless you know exactly which are the dubious answers, which you can exclude just those answers. But what you cannot do is leave them in. And of course, it should go without saying, but I've often seen this, you can't change your criteria halfway through. You can't use biological sex for the first half of the study and then self-identified gender for the second half. And this is not only questionnaire type stuff, this goes for laboratory data as well. Let's say you are reading information from some sort of machine that measures something, okay? And we know it's a little bit imprecise. So what we do is we take 3 readings. Now you can't, for the first 20 observations, record the lowest of those 3 readings. And then for the next 15 observations, record the average reading. And then for the last observations, go back and record the lowest reading again. Everything has to be consistent. It's the lowest for all of them, or it's the average for all of them. Or in fact, one case here would be to record both the lowest and the average, and then you can decide later which one you're going to use. And you might even find some interesting trend between lowest and average. Right. Next point, we're getting near the end, is generalization. Being too general can lose a lot of potentially useful information. Here's an example of a questionnaire. Do you enjoy your work? Now, many people will be conflicted. There'll be something like this. Yes, I love being a doctor, but I hate working at XYZ hospital. So how are they meant to answer that? Yes, because they enjoy their work in general. No, because they're hating their work at the moment because they don't like that hospital. Or should they then just opt out and say not sure? Whatever it is, when you analyze that item, it's actually going to be fairly nonsensical, because the question can be interpreted in so many different ways. You really cannot lump everybody who says yes into one group and everybody who says no into another group, and another group called not sure, who say a large group was not sure that they had chosen the right profession. That would be wrong. Many people wrote not sure maybe because they love their profession, but they're not sure how to answer because they're actually not happy just at the moment. Right. So your data collection sheet should be as simple and intuitive as possible, sufficient instruction, explanation, clarification, and help that it cannot be misinterpreted. It's always best to list the possible answers, okay? But then, as I said, always have a blank space where anything that isn't one of those possible answers can be entered, because it may turn out later that there's something very important hidden in all of those. Right. Other things that lead to error, all of us have encountered this in forms all the time, forms that are just poorly designed. This might, for example, be a typical passport question when you renew your passport. All countries visited in the last 10 years. There's enough space to write one country. What if you're a frequent traveler who's been to 15 countries in the last 10 years? There's only space to record one. Watch out for that sort of thing. Trouble is, when somebody fills that form in for you, some people may just put the first one because that's all there's space for, leaving out the other 14. Other people may be forced to use abbreviations. And when you come to see the abbreviation, you don't actually know what it means. Others may scribble in tiny writing so badly that you can't actually interpret it, and so on, and so on. Another one that saves a huge amount of time is following natural process flow. Imagine you want to extract a lot of information from hospital folders. Now, the hemoglobin and the white cell count will be on laboratory forms. Age, sex, and date of discharge might be on a different piece of paper. So you don't want to have to look at the age, then go to the laboratory form for the hemoglobin, then back to the first paper for sex and date of discharge, and then back to the laboratory form, and so on. Try and group it so that you can work through one set of questions at a time. The more going backwards and forwards there is, the more likely there is to be error, quite apart from frustration. Right. Another time of extreme danger is when your data is actually captured from your sheet, data collection sheet, onto a spreadsheet or into a database. Okay, you may be doing it, somebody else may be doing it for you. It makes sense to minimize workload just to make it easier, but also the easier it is, the less likely there is to be error. So you need to minimize the potential for error, miscapturing, people putting things in wrong. If your p-value is such that it's going to work out to be pretty close to 0.05, okay, just one wrong item captured might be sufficient to push that to 0.55, not significant, or down to from 0.55 to 0.5, which is significant. Okay, a few tiny errors can make all the difference. So as few operations during capture as possible, and exclude any need for interpretation during capture. Your data capture should not have to work out what they are meant to write down. They must just capture what's written there and put it into the database. So the best, of course, is to avoid having to capture anything at all. Most big research projects these days, you'll tap data into a computer or onto your phone, and it's immediately uploaded straight into the database holding all the results. You don't write it down in one place first and then capture it later. So if you're very fancy, you can have software or apps that do that. But of course, always protect your database. If people can upload things directly, then they can deliberately or inadvertently also upload stuff that crashes your database and corrupts all the information. It's potentially very dangerous. Okay. And then the other way is to capture it in formats which can later be imported, but automatically. For example, if your data is captured on one form of spreadsheet and everybody's spreadsheet looks the same, then it is possible for somebody to set up an automated process for importing data from each of those spreadsheets onto one big spreadsheet. Again, it's got to be done by somebody who knows what they're doing, because there's potential for error there. Right. Getting close to the end, goes without saying, protect your database, protect all your data against data corruption, system crashing, data loss, data overwriting, which is a horrendous thing. You make mistakes on an Excel spreadsheet, and then inadvertently you save that over an earlier spreadsheet, which has got the correct data on it. And now your correct data is lost. Okay, and so on, and so on. And always have backup and redundant copies. Whenever you make changes, it's best to save it under a different name. So that if something goes horribly wrong, you can go back to a previous version and work from there. Right. Okay. And another very good thing, quality control, pilot your data collection sheet, try it out a few times, pick up the things that don't work well, the things that are ambiguous, the things that research assistant will misinterpret before you actually start capturing the real data. As the researcher, review captured data exhaustively, item by item. Okay? Make sure that your research assistant has actually captured things correctly. If things look dodgy, do a check, go back and check, question them as to what they did. And the same with your eventual spreadsheet that you're going to do your stats on. You need to look through very carefully. Where are the things that ought to be blank but aren't? Where are the numbers that look like labels? Where are the numbers that have got text written into them? And so on, and so on. And it may be helpful to get somebody external to review your data, because it's very easy for us who are so intimately involved with it to fail to see the problems. Right, and that is that. And I'm available for questions. As you would have gathered by now, this is based not on any sort of reading, but on experience, and very often on somewhat sad, bitter experience. Right. Is there anybody who'd like to say anything? Questions, comments?
Hi there, Prof. Just Sarah speaking.
Hi, Sarah.
Have you got any advice just on, I was looking at my Excel spreadsheet last night. I'm looking at genetic results. Mm-hmm. And so everything's in an Excel spreadsheet. And so there's one column for normal and one column for abnormal. And what I've done is tried to combine them together. So either a 1 for normal and a 2 for abnormal. Is that the right sort of thing to do? I have got multiple copies of my originals, yes.
Okay, it's impossible to say without knowing exactly, what that information is and how you intend using it.
Right.
Of course, no harm is, as long as the information is there and can be separated, no harm is done. If you put it in 2 columns, because it's very easy. In a couple of minutes, somebody who knows Excel fairly well, like I do, knowing formulae and things, can get all that to 1 column.
Okay. Yeah,
Similarly,
I don't know that yet.
In 1 column, you can split it out into 2 columns. As long as it's there, it's okay.
Okay.
When it comes to time for analysis, let's say you were to come to me, then I might say to you, it will be easier to analyze this in 1 column, so let's quickly do that. Okay. I spend a lot of time when I help people say analysis, tidying up their spreadsheet before we start putting in.
Okay.
Sort of things that can go.
Yeah. No, okay, that's what I'm trying to do at the
Some
moment.
forms of data that are better in separate columns. The other forms of data that is best in 1 column. If it's a yes, no, true, false, then it's often best just in 1 column. Sure. Yes, no, yes, no, 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 yes, no, rather than a tick under yes and a tick under no.
Okay. So that's what I'm trying to do, just so that's condensing my Excel spreadsheet into something that's, like that. So it's binary, saying yes or no. There are a couple of unknowns, so I've made it a 3. Oh, sorry, no. The 3 is when reporting male, female, or unknown. So when there was no known result for a gender at the end of the day. So maybe I need to make an appointment with you, and so you can just have a look. But I'm trying to condense it to make it the most sensible kind of way of looking at the data.
Now, you'd be welcome, as long as you understand that, of course, when it comes to actual statistics, geneticists have their own highly specialized forms of stats they do, for genotypes and things like that, that obviously is way beyond my capabilities.
Yeah,
so
it's not that.
Even our college statisticians may struggle with that. It's a highly specialized field, the statistics of genetic work.
Yeah, so this is not actual results and stuff in terms of genetics. It's more in terms, so I did a survey of doctors,
Right.
asking how much they knew about genetics. So, and then I've also got a database of 6 years worth of genetic results. So that's the one that I'm actually working on at the moment.
Okay. You've reminded me of something else, and it's actually an important point. So let me just quickly share my screen again to show that with you. I've just got one thing up on the screen. Right. Okay. You remember this one?
Yep.
It's a complete misconception that you can't write names. You have to replace them with numbers. Okay. So many people come to me, instead of saying male and female or M and F, which makes analysis so easy, they've converted males to 1 and females to 2. Right. Nothing wrong with that as such, except all the analyses you do along the way becomes that much more difficult to understand intuitively as you go. Because you find that 1s are higher than 2s. Now you've got to remember what is 1 and what is 2. Okay, male, female is not too difficult. But let's say we gave the names of the schools, numbers 1, 2, 3, and 4. Okay. So look, the marks are higher in 3 than in 1. What does that mean? Oh, now we've got to go and have a look and work out which school is 3 and which one is 1. Whereas if you had a look here and said, SNPH is higher than SHS, it's very much simpler. Most stats packages these days are perfectly happy working with these sort of labels. Okay?
Okay.
There are a few types of statistical analysis where labels have to be converted to numbers. And the reason is because the actual statistical calculation is based on numbers, okay, rather than names. Various forms of, logistic regression and so on, you have to replace names with numbers.
Okay.
And doing all the classic things like comparing with t-tests and ANOVA and correlations. Software is very happy to compare age, called age, sex, called M or F, with something. It doesn't need it to be 1 and 2.
So I don't need to change all of that. And then can I ask another quick question?
If you've captured it as male and female, and then we discover we want to do a test that requires 1 and 2, well, that's easy. Just quickly add in another column and replace M and Fs with 1s and 2s, and then run the analysis straight away. It's no big deal to do it later if it's necessary, but it's hugely advantageous to interpretation if you have real names there and not funny numbers.
Right. So for that, I've got then 2 columns which I'm amalgamating into one, so I can use the M&F for that. So that's perfect. Then there's another part of my data sheet where I've got doctors' names, and then I've got the profession. So whether it's a gynecologist, whether it's a GP, whether it's a pediatrician, all of that kind of stuff. And so is there a way that I can, so there's probably a fancy Excel way, and I've been watching lots of Excel YouTubes to try and figure out, but is there a way that, say it's Dr. A who's a gynecologist, and then there's a Dr. B who's also a gynecologist. Do I need to combine those to say Dr. A who is a gynecologist, or do I need to, or do I not? I suppose it depends on the question I'm asking. So it's, one of the questions that I want to ask is how many different types of gynecologists or different gynecologists themselves do we have?
Right. Well, is there some sort of information on that? Have you captured whether a gynae oncologist or an obstetrician or a...
Yes, that's all captured in words and doctors' names.
Okay. Then what you want to do as far as possible, as we said earlier, is make sure that they are all captured identically. So if they're an obstetrician, write it out in full, but otherwise write OBS and make sure they all say OBS and not some saying OBS, yes, and so on. Then it becomes very, very easy afterwards. Touch the button, put out all the data we want.
Yeah, that's done. I did have an issue with the doctors' names though, in terms of like a doctor, and then whether you leave a space or you put a full stop, or so I've managed to clean that up as well.
Right. In general, the best of that, of course, is one column for surname, one column for first name, rather than putting it all in one cell.
Okay.
It's just easier to capture, but not that it really matters, because you're not really going to divide people up by their names. Okay.
No, I am, because I want to know. So what I want to correlate then as well is how many samples were received by that doctor.
Right. Well, then, in fact, it probably is best to have everything in one column. Otherwise, we'd have to do a bit of fancy footwork to combine surname and first name from different columns to identify as being unique.
Because there are a couple of different same surname doctors.
So it all depends, on exactly what purpose you're going to put that question to, which is really the point of this talk. As you collect it, you've got to be thinking ahead to what you're going to do with it.
Okay. I shall request an appointment with you if that's okay.
Oh, of course.
Is online fine? Because I'm in Pretoria.
Oh, if you're in Pretoria, obviously online is fine. If you're close by, well, really that much more meaningful to sit together with a cup of coffee and do it. But no, online if necessary.
Okay, perfect. Thank you so much.
Welcome. Okay, anybody else? Otherwise, we'll say goodbye. Bye.
Thank you so much, Prof, for such a wonderful presentation.